Okay, so I have two parts. I first put on my hat as the president of the Power Electronics Society, and then I put on the hat as professor in power electronics and electric machines at the Delft University of Technology. And yes, I will tell you about some of the projects that we have been doing. Just 3 minutes, if you bear with me, just say a few things about PELS. This is the distribution of our members from last year. So as you can see, most of our members are from industry. And then the second largest part on the pie chart is academia, professors and PhD students. We run conferences. So I think with the IEEE does basically two things, main things, conferences and publications. So the IEEE divides the world in 10 regions, and PELS is active in all these 10 regions. We are not doing it alone, so we're doing it with partners. I think you saw some names coming up. So European Power Electronics Society, we have in China 2 partners, Taipei in Taiwan, the Korean Institute of Power Electronics. Also in South America, we have with Sociedad, we're partnering. And of course also with other societies. I think most of you, like me, are also a member of maybe 3 different societies of the IEEE. So first of all, we have our main regional conferences. So there are 3 ECCE conferences. They are the flagship conferences of PELS. And so one in North America, one in Europe, and one that's traveling around in Asia. And the 4th conference is a new conference. The first conference was held December last year. It was in Fortaleza in Brazil. And this conference moves around in the Southern Hemisphere. It's called SPEC, the Southern Power Electronics Conference. Maybe we can also come to Chile sometime. Then there are some local conferences that we're also supporting. These are not only, we have other partners, and sometimes we take the lead and sometimes we are invited to participate. Then there are, I think, the 2 main, and that's also, I think, the biggest conference of PELS is the Applied Power Electronics Conference in North America. This year there were more than 5,000 attendees. And there's a new one in China called PIAC, same letters in the acronym, the Power Electronics Applied Conference. It's held every 4th year, and it's done with the Chinese Power Supply Society. And then many specialist workshops, symposia, a smaller conference. I think you saw all of them coming up. I'm not going to discuss them. We have 5 publications, so 4 journals and a magazine. So the Power Electronics Transactions, the Power Electronics Letters, the Journal for Emerging Technologies, a magazine, and then as from this year, I think the first edition of the Transportation Electrification Transactions. Now, the PELS Transactions, the T-PELS as we call it, is doing very well. So we just updated the information. For a number of years, it has been ranked #1 in the IEEE from usage point of view. So this is an indication how many people are downloading the papers to read them. So power electronics is hot. It is really a very important technology at this time. Google also ranked the transactions on power electronics as #1 in its survey. So now I think putting my other hat on as a professor at the Technical University of Delft. So the title is Emerging Technologies for Renewable Energy Conversion. So just a few things where I come from. Okay, so my 2-dimensional country is much smaller than your 2-dimensional country. It's just a speck on the map. About 40% of the Netherlands is under sea level. That's also what the Netherlands is famous for. So if it was not for the dikes that keep the sea out, this is what the Netherlands would be looking like. So as you can see at the bottom, sort of in the middle of the photo, is Delft. So I think some parts of Delft is just above sea level. In the Netherlands, there are 13 universities. 3 of them do electrical engineering, and the Delft University of Technology, with 13,000 students, is the largest and the oldest technical university. Now, University of Technology means that you only get engineering degrees. Okay, so now renewable energy is making great strides forward. It is also essential that we introduce energy technologies that do not have a large CO2 footprint. So there's also an exponential growth. Now, if you look at the various technology developments, I mean, we can even say at this point that some technologies are maturing. Maybe wind turbines, maybe conventional PV. But in view of how far we yet have to go to improve our planet and make it sustainable, it means that there is a lot of innovation opportunities for game-changing, for disruptive technologies. And this is really what is the topic of my presentation. I'm going to show you some of the projects that we've been working on, and also looking at these projects really from a power electronics and electromechanics point of view, because this is our field. Now, in some cases, we are very enabling, essential. I think power electronics is essential to make any energy system work nowadays. But in some cases, it can also really change it, make the technology more attractive, or actually being leading introducing the technology. So I think what I will. So I'm going to discuss disruptive, discontinuous, sustainable innovation opportunities, review some alternatives, and I'm also sure, I hope, that maybe all of you will hear about something that you've not heard before, some new kind of renewable energy systems. So the content is, I think, first of all, simplifying the mechanics of wind turbine, that's number one, then electrostatic actuators for energy harvesting, more integration of photovoltaic conversion, and then finally the conclusion. So okay, there are 2 topics I'd like to discuss about wind turbines. First is, let's say, direct drive generators with magnetic bearings, and secondly, brushless doubly fed induction generators. So I think this is a picture that you may have seen before. This is the growth in the size of wind turbines. There's a clear advantage in scaling up the size of wind turbines. And I think at this point we are already, I think, at this 10 megawatt big Vestas wind turbine that was introduced a year or 2 ago. So this may be a familiar picture for some of you. These are the different types of wind turbines. I mean, the first generation, and there are still many of them in Denmark, also in the Netherlands, a couple, which are the constant speed, so basically a squirrel cage induction generator. Then we have the variable speed with gear. That's the doubly fed induction generator. So it's the induction machine has slip rings, and the power converter rated about 1/3 the power then controls the power flow through the rotor. And the last, and that's the direct drive. So with a direct drive generator, it's a generator that turns at a very slow speed. It doesn't have any gearbox, which has some advantage regarding reliability, and then a fully rated power converter. Back-to-back power converter, connecting the variable frequency coming from the synchronous generator to the constant grid frequency. So, yeah, direct drive, it's called the all-electric approach. Get rid of the mechanical gearbox. It is really a challenge for force density limits because you have enormously large torque that the machine has to handle. So this inevitably results in a large diameter. There are some major issues. The one is the active material protection. You've this very large diameter. How do you protect it? Remember, there are also magnets in some cases. I think then the key issue is really you have to maintain a small air gap. For any machine, a small air gap is essential. So and this also then brings us, because of these issues, to the weakness of the direct drive, and that it is heavier. This is what this graph shows. At the bottom, it's a doubly FET generator, mass in tons, and the top, it is the direct drive. So how can we solve this problem? First of all, let's look what scaling does. And here you can see a number of lines. There are some equations about the scaling on the right-hand slide. And there's a problem with the connection, so we just close it. So I think the purple line is the total mass, and then the blue line is the active mass, electromagnetic active mass. And as you can see, the scaling is linear for the active mass of the machine, but it's to a higher order for the structural part. The structural part is really the red line. So we need to find a solution. Now there has been some approaches, obviously. I mean, there are many of these direct drive machines out there. So there's a hollow stator structure, for example, the Enercon E126. You can make it like a bicycle wheel with spokes. That's an alternative, the sway turbine. And then there have also been some concepts like, in this case, installing little wheels. It's like a train that goes around, and in this way you can control the air gap. Now the option that we have chosen is using magnetic bearings. So there are then a few features. Okay, you still need a strong rotor ring. You make it stiff. You have a mechanical bearing, a thrust bearing that takes then the forces coming from the wind. But really the machine's part, this air gap, interaction between the magnets and the windings, that interaction, that distance we control with magnetic bearings. So here you can see the example, one basic implementation in the full-scale system on the left-hand side, and then the lab unit that we built. Now I think important here to realize is that, okay, it's 5 degrees of freedom that you have to control, which is a tough control problem with magnetic bearings. Now, it can be done. I mean, magnetic bearings are applied in many applications, mechatronics, high-performance mechatronics applications. But there's another alternative where you can reduce the degrees of freedom that you have to control just to 1. And this is the concept of having a buoyant rotor. So okay, I don't have a pointer here, so I think on the left hand in the corner, top corner, you can see the basic control system. So there's one-dimensional control. And if you can see here at the bottom, you can see it's all filled up. We have the rotor, the stator structure, it's inside each other. The space is filled up with a very low viscosity liquid, giving it the stiffness. And then just this position of the internal and external part is controlled with this magnetic bearing. On the right-hand side, you can also see the system as it was implemented in the lab to demonstrate it with, thank you. This is the light. So this is the lab, the demonstration in the lab. Though this was coming actually from a PhD, an idea from a PhD student from Korea. He went back to Korea and he built the system. Now, I think the second topic on reducing the mechanical problems in wind turbines, and that is the brushless doubly fed induction generator. So the conventional doubly fed induction generator uses slip rings to get the power from the rotor. Now, of course, slip rings are prone to wear. It's also a cause of fire. I mean, there's all this carbon dust. So some of the fires that occurred in doubly fed induction generators were directly related to the carbon dust. So there is an alternative, and that is the brushless doubly fed induction generator. It uses 2 stator windings and a special rotor construction, a nested loop rotor winding. So it provides 2 advantages. First of all, the speed is reduced, so you can just use a single stage gearbox instead of a double stage gearbox. And it has the feature that if there's a fault, so a voltage dip, that you can ride it through. That's one of the weaknesses of the doubly fed induction generator, that if there's a voltage dip, you get an overcurrent situation in the rotor. Now, it's not new, like many things in machines. So this shows the, it's basically based on the cascaded induction machine coming from more than a century ago. What I show on this slide here, here we have one induction, well, it's basically 2 induction machines on the same shaft. The rotor is connected to the stator, and this rotor is connected to a rheostat. And you can see the curves of the 2 machines, a 4-pole and a 2-pole machine, and the combined machine gives you a lower speed. Now you can play around with this concept. First of all, instead of connect the 2 rotors to each other. Now, of course, this can be done internally, so you don't need a slip ring, get the advantage. And the next step is just build one machine with a special rotor, so this nested loop rotor, and you end up having 2 stator windings. And of course, then we can use power electronics, and so the one stator winding is connected to the grid, and the other one is then connected to the back-to-back converter in the same way as the conventional doubly fed induction generator. So this is the unit that we have in the lab. Now we must also recognize we're collaborating with the University of Cambridge. I think they're really the leading group in this field. And in this unit we actually applied sensorless control. And just a nice picture. Okay, how do you model it? It's actually a very interesting machines modeling and design challenge. Okay, so now we go to the next topic, and this is about photovoltaics, and call it integration of photovoltaics conversion. Now the first is, sorry, I think I'm missing, no, sorry, reset. Still the second topic is electrostatic actuators. And now this is an artist's impression of electrostatic wind energy converter. We call it the AVCON. It's basically a grid on a pole at sea. And some architect was very inspired, so he said, I mean, he will build a building with this grid in the middle of the building. So called the Dutch windmill wheel. So what is this? So it is using the principle that, if I can explain it in short, that, okay, you have the wind, you charge droplets, you release these droplets in the wind, so they pick up the kinetic energy from the wind, and then this grid that we have, that grid presents an electric field that slows the droplets down. So basically converting then the kinetic energy of the droplets into electrical energy. And these droplets with a charge then get stuck or is caught at a very high voltage, maybe 100 kilovolts. And then we have 100 kilovolts charge, and we can feed it through and generate power. So this was the proof of principle in the lab. I think in the back you can see that's the wind generator, so we need to make some wind. That's a high voltage, so this mesh or this grid is on a high voltage. And you release then, I think with these little jets, the droplets, the charged droplets, to slow them down. Okay, so basically, so what we get, I think what we expect is if you have a large, maybe 50 by 50 meters mesh, that it will generate about 100 kilowatts from between 50 and 100 kilovolts. So what would the power electronics look like? Now, the rating is similar to X-ray high voltage power conversion systems, so for Röntgen equipment for medical purposes. So this is X-ray converter. The X-ray converter, we take three-phase AC, we step it up to about 100, 150 kilovolts. It's a converter that's fully submerged in oil. There's also one that we built in the lab for a project. And now, okay, so you just have to do the inverse, going from high voltage to low voltage. Interesting thing is there are not really topologies. I mean, we have the Walton Kraft, it's a very well known, but if you go from high voltage to low voltage, there are really no applications where you do that. So I think that's a challenge. Okay, the second is wave energy. This is a project that we participate from SBM offshore. And it's the electroactive polymer wave energy converter. And here you can see the basic concept. So you have basically a tube with this polymer. So it's the same material that you use to make plastic capacitors. These, this is then an expandable. And then as the waves pass over this tube, some parts of the tube are contracting, some parts of the tube are expanding. And then this contraction expanding principle is then used to generate energy. So basically this tube is then divided in various segments. Each of these segments are basically a capacitor. So now if you go to the next slide, so we get then these expanding, contracting capacitors. And of course, if you expand and contract a capacitor, the surface area becomes larger and the distance becomes smaller, so your variable capacitance. In the stretch mode, it has a large capacitance, a low voltage. It's basically the low energy state. If it's allowed to contract, then the capacitance becomes smaller, the voltage goes up, and it takes mechanical energy and converts it into electrical energy. So here on this graph, we show the electric operation. So first of all, this is the capacitance as it varies as a function of time, becoming smaller, larger, smaller, larger. On this graph, you see the current. So at the right timing, critical timing, we place then some charge on the capacitor. For example, when the capacitance is very large, then we charge it. Then I think the voltage increases. And then when the voltage is a maximum, then we discharge it. And in this way, we get power. So you basically run a cycle here. This is the stretching. This is the energy. And the area of this cycle gives you the energy that you recuperate. There are, I think, three possibilities. One is constant voltage, constant charge, constant electric field. Now, the constant electric field, that gives the highest energy yield. So electrical specification is the voltage varies from a low voltage to 10 kilovolts. One segment will deliver about 5 kilowatts. So having 20 segments will give us 100 kilowatt generator. We designed and built a converter. And so this was basically a modular dual active bridge design. You can see the experimental prototype on the right-hand side, and this project is continuing, so there's a lab model, large big lab model to run the full system. It's currently being investigated. Okay, now I get to the integration of photovoltaics conversion. So we will discuss two topics. The one is panel integrated PV converters, and then solar field. So I think you're very familiar with PV. So I think most of the current commercial large-scale systems look like this. It's a PV array with a lot of series and parallel connected PV modules, centralized maximum power point tracking, and it has then a power curve that you can see on this graph. Now the problem is, I think as you are aware, that okay, if some dirt is deposited on these PV panels, their characteristics change. They are not, and you don't get an optimum performance of the system. So it will derate according to this green curve. Now, the way to get around the problem, and this is also used, is to have multi or individual maximum power point controllers for each solar panel. So in this way, we can eliminate mismatch losses, and it also increases the flexibility and modularity. So we will get more power if there is some degradation of the individual panels. Now, these micro PV inverters are applied. I mean, these are some photos, and they exist on the market. Now, what's the problem with these PV inverters? How can we further improve it? It's again getting back to the ratio between the active material that do the job and the non-active material. What's the non-active material? It's the packaging material. So in power electronics, I think we have a lot of material that costs a lot of money, and it's a little bit like chocolates. I mean, what you want is really the chocolate in the middle. And I mean, you have a plastic wrapping around the box. You have to take that off. Then you have to open the box, and then you have these chocolates there, and you also have to wrap them. And you end up with a huge pile of wrapping when you're finished with a box of chocolate. So how can we improve matters? So that would be to integrate the converter in the PV panel. In this case, we investigated then flexible, thin film PV modules. So the challenge is then to build a low-profile, flexible, integrated DC-DC converter. The main issue that arises is the fact that the PV panel and the power electronics converters are now thermally coupled. So, problems, we don't have any normally heat flow at the backside. The efficiency of a PV panel is maybe 20% if you have a good one. So there is 80% heat that is going somewhere. So I think the investigation is then to first of all determine the hotspot, look at what the temperature profile looks like. Then the second step is to build a suitable converter. Now this converter has to be flat, and the important component that has to be modified to become flat is the magnetics. So in this case, plastic magnetics of plastic ferrites were used. Plastic ferrites, unfortunately, are not very efficient, as this graph shows. But this was, I think, completed about 5 years ago. This was one of the very first gallium nitride applications of converters that were published, just as gallium nitride became available. So this is the one. The other one is basically a low-voltage converter, where the efficiency is about 90%, the same thing. So these are the two converters that we built. Okay, now also watch the time. We get to solar fuel. Now, the idea of solar fuel is to convert photons directly to electrons, to protons. So converting light into hydrogen without having an intermediate step. So this is a sort of artist's impression. So the whole idea here is that a tandem solar cell is used. So the various layers of the solar cell are then selective to different frequency or different colors. So I think the ultraviolet and the blue is then used for the electrolysis, and the green and the yellow and the red is then for another solar cell that then captures the full energy coming from the light. So what would the application be? So this idea is that you have a big array of solar panels. With these solar panels, you generate hydrogen. This hydrogen is then going through this water shifting process. And what comes out is then hydrogen and carbon monoxide. It goes through the Fischer-Tropsch process. From the Fischer-Tropsch process, we get methane. Methane is stored in tanks. And now if you just wait for the methane to follow its path, you see the methane then goes to a generator. This generator would generate electricity. So, and the carbon is then recycled. So then we have basically a large power station, that dirty, high carbon power station. We capture the carbon and we then recycle it, and using solar energy to capture carbon in a very productive way. Okay, this is the basic conversion. I think you may be familiar with this. I mean, we have a PV cell. It has a 20% efficiency. We have electrolysis process. That's about 75%. The overall efficiency from photons to hydrogen is 15%. So, and the current cost is about 36 euros per kilogram for conventional systems. Now, I think the goal is to reduce it by order of magnitude by applying a new technology. Now, just give you some, maybe just a little bit of chemistry. So if I have an electrolyzer, what does it look like? I mean, it basically, to do the electrolysis process, I need a potential of 1.2 volts to do electrolysis. So here this is what I showed you. Here's again the picture of the system. So I'm just repeating again. Here we have the water. There we have the cathode. And then here we get the electrolysis reaction. And some of the light then penetrates. So it's a special solar cell made from bismuth. And at the back there is the silicon solar cell, or two silicon solar cells. And we have then electrons moving around, basically supplying the hydrogen conversion directly from the solar cells. From an electrical point of view, this is the characteristic that we need for the solar cell. And this is the characteristic, basically a diode curve on the electrolyzer, which has then an internal voltage of 1.2 volts. Now, these are material scientists. I mean, they build fancy systems, and they, I mean, in their mind, they have a direct connection between the solar cell and the process. So nobody, at least at our university, ever thought that this box A need not be an ammeter. It could be a power electronics converter. So, okay, let's analyze the problem. We have our reaction potential of 1.2 volts. We need to generate at least enough voltage that we can overcome the resistance of the circuit. So we need this overpotential of 0.8 volts. And we do this then in a two-step process. First of all, the photoelectrode gives us 0.6 volts, and then we need two solar cells in series. And for a system, if we use let's say crystalline silicon, the conventional solar panels, We would have 100 centimeter units. Each 100 centimeter unit would then have an equivalent circuit, as you can see here. These 3 voltage sources, a current of 1.2 amps going into the electrolyzer part. So what we could do, we can then have our basically maximum power point tracker. We have then 2 options. First of all, we can simplify this whole PV part by having a boost converter, just having a single 0.7 volt solar cell, boost the voltage so that it reaches 1.2 volts. Or we can string up more tandem cells and then use a buck converter. And this buck converter, in the same style, it could be size of a stamp. It's a very small power, 2.5 watts. So maybe we can, it looks like a postage stamp, and we can stick it on the back of the solar cell. All right, so that brings me to the end of my presentation. So just to conclude, I think the main message I have, I think that in view of the importance of renewable energy and the scaling that is still needed, there is opportunity for disruptive and innovation. I think there is a trend to go more electric so that you get rid of the mechanical problems, the gearbox, the slip rings. Electrostatic actuators present an entirely different approach, but it is very immature. It's on a very experimental level at this time. And the third is that one can reduce the cost of PV conversion, the normal PV systems, plus also something like solar, let's say solar fuels, by using integrated power electronics. Thank you.